Take it away.
Hi, so I'm Shashir. I'm a second-year graduate student at the University of Southern Queensland. I'm going to be talking a little bit today about some work I've been doing to study the occurrence rate of planets around M dwarfs with TESS. So a bunch of people have already talked about why cool stars are cool, but just to emphasize, cool stars are the most common stars in our galaxy. We know that planets around them are very frequently terrestrial, and those terrestrial planets are also very frequently temperate. And from an observational standpoint, cool stars also represent the best opportunity right now with current instruments of studying the atmospheres of both terrestrial planets and temperate terrestrial planets. And so cool stars are a particularly good sample if you're interested in studying atmospheres. And if you're interested in demographics, cool stars are also very interesting. So just to go over some of the work that's been done on this before, Kepler provided great demographics for FGK stars, and it even sampled into the early M dwarf end, and some very foundational work by Dressing and Charbonneau has presented occurrence rates from these early M dwarfs. But TESS provides far more mid and late M dwarfs. And some people have also done work on this, Ment and Charbonneau, to name one. They basically looked at a smaller sample of M dwarfs in TESS. That's a very clean sample. I'm interested in doing this on a much larger sample. So if you're interested in demographics, of course, there's multiple demographic features that are expected to occur for planets around cool stars, because planets around cool stars probe lower insolations. And any effect that's dependent on insolation will be very interesting to study around cool stars. So for example, you can ask the question, is there a different demographic distribution of planets that form outside the ice line versus inside the ice line? And the ice lines of planets around cool stars, or the ice lines around cool stars, are accessible with transits. Of course, if you're interested in the radius valley as well, that may be, depending on how the radius valley is sculpted, that may also be insolation dependent, and you can study that in this sample. And so we take a sample of 44,000 M dwarfs with TESS 2-minute cadence data. So we basically cross-match the TESS cool dwarf catalog with those targets that are observed in 2-minute cadence data and targets that are less than 3,500 Kelvin. And so here are some histograms of our sample. Basically, we have distance first, and then TESS magnitude is the second histogram. And the third histogram is the effective temperatures. So we're mostly sensitive, or most of the targets in our sample are mid-M dwarfs and some late M dwarfs as well. So from this, we can, of course, do our planet search. I won't bore you with the details of our planet search. It's pretty standard. But basically, we do our detrending, we do our flare removal, and then we do 2 BLS iterations, one on the short period end and one on the long period end, in order to obtain a sample of planet candidates, which we can then vet. And so after we do this, we do a suite of injection recoveries. So for those of you who have dealt with TESS data, you'll know that occurrence rates with TESS are very difficult, a lot more difficult than Kepler, because of the scanning strategy of TESS. So basically, this means that there are gaps in the time series. Transits may fall in the gap. The recovery fraction versus SNR curve is less trivial than it is for Kepler. And so in order to address this, we do a suite of 50,000 injections and recoveries on a subsample of stars. And then we can bin the recovered fraction by SNR in order to come up with a kind of empirical recovery fraction versus SNR curve. So normally this is just fit to a logistic function, but we should do this more empirically, because you can see that it doesn't ramp up the way that a logistic function does. And so we can use this, of course, to apply our completeness corrections. So when we do that, this is what we get. And from our completeness corrections, we can then take our sample of planet candidates and then obtain an occurrence rate. So the way that we do this is with Cosmo ABC, according to the method of Kunimoto and Bryson. And this is like basically an approximate Bayesian computation. So it forward models the data and then uses that in order to obtain an occurrence rate. So I'll stress that the occurrence rate that we obtain from this is preliminary because there's still work that we need to do on our reliability estimates. But I'm going to present the occurrence rates right now and not interpret it too much. And you guys can interpret it the way you'd like or ask me any questions that you have about it as well. So this is a preliminary look at the occurrence rate from our candidate list. Yeah, I guess I can leave this up there just for you to take a look for a bit. And one thing that we get from these from this search as well is a sample of planet candidates. So there's a couple of planet candidates that are particularly noteworthy that I'd like to go into. And these are the vetting plots for those 2 planet candidates. The first one is Gliese 12b. So we published this last year along with another group, and it's particularly exciting. It's an Earth-sized planet around a mid-M dwarf that's only 12 parsecs away. This is a little bit closer still than the TRAPPIST-1 system. And the planet Gliese 12b has an orbital period of around 13 days, and an insolation somewhere in between that of Earth and Venus in our solar system. And that gives an equilibrium temperature of around 280, 290 Kelvin. So when we found this planet, we basically decided to go out and obtain a bunch of ground-based observations. So we get, of course, the test data. We also proposed for KOPS, and we got multiple visits of KOPS. And then 3 ground-based facilities we also used in order to get the transits. So these are the transits from all of those. Gliese 12b is particularly exciting because it is one of the most amenable tempered terrestrial planets for atmospheric study with JWST. So for those of you that are familiar with the TRAPPIST system, you know that one of the challenges with the system is that the star TRAPPIST-1 is very active. It flares a lot. It's very spotty. It's a typical late M dwarf. But Gliese 12 is actually a mid-M dwarf, and it's considerably older, so its activity level is a lot lower. In fact, we don't observe any spots or any flares in the entire test baseline. And this makes it outstanding if you're interested in studying the atmospheres of terrestrial planets without the contamination that you'd get from those spots and those flares. So there's already an HST program that is attempting to study atmospheric escape. So as I mentioned earlier, this planet is in between the insolation of Venus and the Earth. And we know that Venus underwent a runaway water loss sometime in its history. And this planet being in between Venus and Earth gives us the opportunity to study that process if it were to occur on this planet. And so if that process is ongoing, that might actually be detectable in Lyman alpha, which would be very exciting. So here's like a little parameter space plot. You can see that, I don't know if you can see my cursor. I guess I can use this. This is the TRAPPIST system. Gliese 12b is up here. And so it is much brighter than the TRAPPIST system, and it's also in that unique area of planetary insolation that we're interested in studying. The other target that is exciting is LHS 6050b. So this is a 2 Earth radius super-Earth, and it's very cool at 200 Kelvin or so. It has a 40-day orbital period. The host is another mid-M dwarf that's only 20 parsecs away. And our group has an espresso program to obtain the mass that is currently ongoing. The exciting thing about this planet is that it's a cool water world. So there's a lot of exciting science that's being done on water worlds right now, especially warmer water worlds that show some interesting atmospheric features of these water worlds, especially in trying to distinguish whether they might be water-rich or whether they are primarily helium and hydrogen dominated. So it's expected that these kinds of water worlds would stratify at these cool equilibrium temperatures. And LHS 6050b presents the opportunity to study that process if it is to occur. This planet is also near the M dwarf radius valley. So it's very interesting to study the process of photoevaporation and study how planets of different insolations might have their radii sculpted differently. And so with that, I'll leave up some summary slides. There's a lot of work that, that is still yet to be done in this. For one, there's FFI data. I've used the 2-minute cadence for this, and that FFI data is still waiting to be analyzed. And there's additional work that we're going to do to improve our reliability estimates. But stay tuned for the upcoming paper for that, and we'll have some finalized occurrence rates that we can present to you. Thanks. Oh, yeah, thanks.
And actually, could you read aloud the values in those lower right boxes there? Just so
yeah. I think that's a 46.77 plus or minus, or plus 27 minus 12, 6.16 in the next box, and then 26.21 in that box over there.
Okay, questions? Yeah.
Great talk, Kevin Harder-Gilman, IPAC. Have you, I know this is preliminary work, have you done any comparisons of your sort of mid-later M-dwarfs to the earlier stuff with Kepler and I think an early result with TESS with like 7 planets in their data set? Have you done any comparisons yet?
Yes, yeah. So we've, of course, been looking at the Dressing et al. Occurrence rates from Kepler very closely and like extrapolating that to our sample and seeing how it compares. Right now, we're getting like higher occurrence rates, and that may well be because our reliability estimates are off, or that there are like basically planet candidates in our sample that aren't real planets yet. So as we improve those numbers and improve our vetting, those numbers may change, but yeah, that's like, I guess, a comparison. We're also, like I mentioned, we did a short period and a long period BLS. These are the results from the short period end of that primarily. And so the long period BLS will also like allow us to kind of compare our results on the longer period end beyond 50-day orbital periods to the Kepler sample, if there's anything in there.
I have lots of questions, so catch me later.
Actually, let's go first there and then there. So first here.
Hello, Shashir. I'm Dom. I'm also a young researcher doing test occurrence rates. Cool. So I have a bunch of questions. Let's catch up later. Yeah. But the first one is about multiplicity. In your search, did you mask out initial signals and then research to have planet multiplicity as a factor, and then is that taken into account here? That's
actually one thing that we're yet to do. Okay. We haven't masked out transits and like attempted to do an exhaustive search for multiplicity. But that's something that's actually really high up on our priority list right now. The other thing is that SNR versus recoverability fraction curve needs to also account for multiplicity in some cases as well, and for the number of transits. So those are 2 items that are really high on our priority list right now.
Thanks.
Yeah.
And then last question.
HS 6050b is a water-rich planet based on the information currently in hand?
Well, I guess we're not sure that it's a water world yet. It's a super Earth, right? And that could be, it could be hydrogen helium dominated, it could be water dominated. We'll need like atmospheric spectroscopy to distinguish between those 2.
Okay, great.
Oh, yes, thanks.